to scale to a lot of millions of users and billions of data items. And I also hope that you can get some ideas how you can use this amazing database in your own project. So a bit about me. I'm a co-founder and former CTO of Plurk, which is like a huge social network in Asia Pacific. Plurk is still ongoing, and it has like millions of users and billions of data items. And actually scaling it has been a huge challenge. And Plurk is like a Twitter-like service. So you can see it like as a Twitter for Asians. I was from the beginning working with Plurk, and I have helped it build to like support millions of users and billions of page views, and its monthly page views. And Plurk currently stores more than 8 billion unique data items. It's only recently we did like get venture funding. So most of this was scaled using very, very low budgets. While some of our other competitors, like Twitter, has like $1 billion funding. We did not have this. I'm not currently doing any work on Plurk, and for like the past year I have done another company that's doing Todoist and Vdoist, which is like task management and project management. So that's a bit about me. Yeah. So what I will talk about here is some of the general optimizations that led to our usage of Redis. I think we were one of the first huge services to actually use Redis in production, and why we were forced to do this. And I will also like tell you a specific optimization we did to reduce the load and reduce the problem scope. Because I mean, when you work like with huge amounts of data, then you need sometimes to solve them in creative ways, and sometimes you need to cheat. And I'll also tell you how like Facebook and Twitter cheats as well in this, because it's not that solvable problem. And it's basically like Plurk timelines that we will address here. Then I will go into details about Redis and some of sample Python libraries that I have done and that you also can do. And it basically shows like the greatness of Redis in terms of what data structures you can build on top of it and how you can use it in your own project. So I think that's like what makes Redis special if you compare it like to MySQL. On Redis you can build amazing things on top, and you can do it like using 100 lines of Python code. With other databases you have to like fight with the database to build something on top, and it's not that easy. And then I want to also introduce a library that I published and open source like a month ago that use Redis Bitmaps to implement a very advanced analytics suite on top of Redis. And with this library and database, you can do amazing things such as cohort analytics. Yeah, so that's the outline of the talk. So I want to tell you the journey and how we ended about using Redis, and we actually used different databases to solve the same problem. So I know like a bit about where Redis really shines. So one of the huge problems in social networks, and if you look like at most social networks such as Twitter, it's exponential data growth. This means that when you get more users, they get more connected, they share more data, and you need to replicate more data. So you can get like you can very, very quickly get in a state where data grows like exponentially with a small data factor. And scaling this is never a situation you want to be in, because like it does not matter what language you use or what database is used. If your data grows exponentially, then you have a serious problem. And some can solve it, like Google and Facebook, but they solve it using like millions and millions dollar budgets and millions of computers. So if you have that kind of funding and that kind of hardware, then yes, you can probably like solve this in a smarter way. But that's not what we had. So we did not have like $1 million funding that we could just, spend on hardware and then just say, okay, we forget this problem, we move on. So we had to actually come with a solution to this. And right now, Plug does have funding, so it's not a huge problem right now, but when I worked there, we did not have resources to buy a lot of hardware to solve this hard problem. So the smarter solution, and it's really like in general terms, is when you solve problems, then maybe instead of looking to switch MySQL with Redis, maybe you can switch your approach. So you use like a smarter way to solve your problem. Because sometimes it's not really the software or hardware that's the problem, it's really your solution. For us, we actually attack a lot of the problems we solve in really, really great ways. Was basically find something that grows like really, really fast. Find a smarter solution that does not grow that fast. And sometimes when you solve problems like this, you have to do compromises. Because of course you have to cut something to go for like an exponential data growth to linear. So I want to show you how Plug works, so you can like just get an idea what the problem is. So Plug is basically like interactive timeline where you have messages from your friends. And then you can like browse back in time. So you can see this as a Twitter feed of all the messages that your friends post. And then each message has also like responses. And everything here is in real time. So it's like a very, very interactive experience where you chat with your friends in real time and you post a lot of messages. So actually one of the things that was really hard to scale was this timeline. Because you have like thousands of messages coming into your timeline. And you have like millions of users that have these timelines. And you have to populate them with data. So, and the timeline, like the data, if you do this, and another thing you need to think about is that you can't really do joins in this because the database is sharded because you can't have the data on one server. And the data also, if you solve this in a very, very like not smart way or like the naive way, is that it grows very, very fast. So like it's very easy to have like gigabytes or terabytes of data quickly. So how did we solve this problem, and how does Twitter or Facebook also solve this problem? I mean, if you actually go on your Twitter feed, it is capped. This means that you can't infinitely scroll back in time. And there's a very, very good reason for this, because if you can't do that, then the data grows simply too fast. So how did we solve this? We cheated. So how did we cheat? We found out that most users are only interested in recent messages. And nobody really scrolls back like 1,000 messages or even 500 messages back in time. So basically you kept and you're only interested in recent messages. Right? So what does this solution bring us? It brings us fixed size per user, and it also brings us constant time of insertions and updates in timelines. And on top of that, we can also cache this, and we can do stuff like merges of timelines or comparing timelines and all other kind of things that would be very, very expensive to do if you have like, I don't know, 100,000 messages that you need to updating. And I think that was also one of the strategies that Twitter really did that improved their performance, because in the beginning they did not have this. And when you don't have this, then the data grows very, very fast, and it does not matter how much funding you have, you can't solve the problem. So here is really our evolution of the timeline database. So we started with MySQL, and Plurk still uses a lot of MySQL. But at some point we hit the problem, because updating, like doing millions of updates in a MySQL table is not that fast, and you can't do a lot of things in it. So the solution we did was to implement our own database called LikeCloud, which is actually also open sourced. It's basically a distributed key value database built on something called Tokyo Tyrant. So Tokyo Tyrant is basically like a key value database that you can access. And we built actually this in Python. So you can check it out. And we still actually use this in Plurk, but we don't use it anymore for timelines. Because at some point actually we found out that like Tokyo Tyrant was not performing that well on the, like when you do millions and millions of updates, it begins to perform rather badly. And especially if you begin to hit limits with how much you can have in memory. And if it begins to use the disk too much. So the thing we actually found out was that when you need to perform, you should just stick to memory. Because if you just begin to use the disk, then it's already game over, and all performance will be lost. So actually, that's one of the reasons why I think Redis is so good, because it forces you to have everything in memory, and it also means that the performance will be great doing that. And that's basically the biggest selling point, I think, about Redis when you compare it to other key value databases, is the others, they promise you that you can actually scale very easily, but this promise is false, because if you begin to hit the disk, then you can't scale anymore and the performance dies. And also, like, Redis performance is amazing compared to the other, because it does not exchange things to the disk and load and save data all the time. So it just saves the data as you configure it, and it's probably like every second, or it flushes the changes, or maybe like every 10 seconds. It depends what you want. And I think actually that's a great approach, because we tried to use the other approach, which is basically that you have some of the data in memory and some of the disk, but when it actually begins to swap, then it's just a false save. So another thing about Redis that I really love is that it operates on rich data types. And I think, like in other databases, it's really non-natural to programmers to work with like schemas or columns or column families. It's much easier to work with like sets, lists, bitmaps, and key values. And you can use this to build stuff on top. And I will show you how we have built different, or I have just built some sample things that you can use, and we actually use in our code something that resembles that. And every time we have like a problem that we know we can solve using a custom database, Redis is probably a very good bet that you can solve it. But of course, I mean, it's not for all problems that you can use this. So I want to showcase a little open source library called Redis Graph, which basically implements a Reva, and it makes Redis data types are available in Python using Python-like syntax. And it's implemented like, most of the code here is implemented in like under 1,000 lines of code, and this is only like hundreds or 100 lines of code. So basically, we have a wrapper here that wraps a list, and we can use this list as we would use Python lists. But the great thing is that this list is lazy, so basically all the data is stored in Redis, and it's also atomic, so if you update this, then it will be updated on Redis, and if another process loads this list, it will load the updated list. So you can use like length, and you can use membership or the int operator to find out if an item is in a list. The same thing can be done using hashes. So basically, you have a wrapper of a hash or a dictionary, and then you use this dictionary the same way as you use a Python dictionary. But the thing is, everything gets transformed to Redis library calls, and it's atomic. So it's just a nice way to work with Redis, and it's almost like working with Python. Like the database is hidden away. And the same thing can be done using Python sets. So yeah, this is just a small thing. And another thing that's built on top of Redis Graph, but you can also build this using standard Redis library calls, is Redis Graph, which implements a very, very simple graph database on top of Redis. And this is also implemented in Python. And the thing is, this is implemented in under 40 lines of code. So you don't need to code a lot to get something out of this. And actually, there's a real world usage of this. I don't know how many of you use LinkedIn, but LinkedIn has a feature called Who is Connected to You, and you can see how many links are between you and another person. And actually, the way they have implemented this is using an in-memory database of all their members, because no other database can actually answer these kinds of questions that fast. So you need to use an in-memory database to actually solve this problem. And I think if you wanted to solve this problem right now, we can probably use Redis and implement a custom database, and where you have all your members inside it, and where you can ask questions and get answers. So let's look at the usage of Redis Graph. So basically, you can add edges between nodes. You can get neighbors of a node, and then you can delete edges. And then you can also set node values and set edge values. So I think this is like a very, very simplified graph database, and you can use this to build something that's specific to your application or to your problem domain. And this is actually the whole implementation of this. And as I see it, like in most of our code where we use Redis, most of the implementation is really, really simple, because we work with rich data types, and these data types are natural to us. Another thing, and this is actually something we use, we don't use this simple queue, because this is just an example. We use a bit more complex queue, but it's basically the same. We implement a queue on top of Redis. It has amazing performance. We can extend it in any way we like, and it's probably like under 100 lines of code. So if we want a feature, we can add it in 10 minutes or 20 minutes. This queue processes millions of tasks on Plurk, Todoist, and Redoist, and for Plurk it has processed billions of tasks so far. So it's like a very, very high performance and very reliable solution. And it's also very easy to scale this, because if you work with code that's 50 lines of, you can easily add like multiple queues, add some kind of partitioning, and do this in very, very few lines of code. And you can also view this implementation. But basically, the API is very simple, so you can like put jobs, you can reserve jobs, and you can get some stats and delete some jobs. So it's basically what you need in a queue, and you don't really need, I think, a queue service like Zero and Queue or something to implement something that's amazing. You just need something simple. And this is the actual implementation. So this is like high performance. You can probably like process hundreds of thousands of jobs per second if you have enough hardware. And this is atomic, and you can extend it in any way you like. And for me, it's really much easier to work with code like this than work with code bases that like 10,000 lines of code where you don't really understand what is happening. So now I will talk about Bitmapist and Bitmapist cohort, which I'm really excited about, and I think a lot of people can use this, and I have not really seen many use this. So basically, what it implements is an advanced analytics library based on Redis bitmaps. I will cover bitmaps a bit, but yeah. So I want to tell you how or why we implemented this. So the thing you want to do when you have like a website is you want to track retention. And Mixpanel, I don't know how many of you know Mixpanel, but it's a pretty popular solution to track these things. So basically, it can show you some nice visualization of different things. And the thing I wanted to do is have retention. So for instance, I can see a user that signed up on a specific date, like October 21st. How many of them signed up on this day and came back and did an action? So you can see this as looking over time and looking how different things affect your users. So for instance, it could be that you introduced a really, really bad new thing on a specific day, and using this you can see that how it has affected your data, and you can actually filter in this based on actions. So for instance, you see that retention for playing a song is really, really bad after you introduce a new feature, or you see that you need to work more on this, and then you work more on this, and then you can see in the data how has this improved our retention based on a feature or based on an action. So I wanted to implement this, but the problem is for my new companies that we actually do, we are already pretty popular, so we do a lot we have a lot of users. So actually to get this solution, we would need to track like millions of data points per month. And using this, we would need to pay like at least $2,000 per month. And I didn't want to pay this because I thought there was a better way that you could implement this and a cheaper way. So that's why Bitmapist was implemented. And Bitmapist and Bitmapist cohort are both open source, so you can use this in your own projects and save a lot of money. So what can Bitmapist actually help us with? It can, Bitmapist cohort, the thing you see here, the visualization you see here are cohort analytics. But Bitmapist is the underlying tracker that powers these cohort analytics. So basically, we can answer questions such as, has user 123 been online today? has he performed action today? Has he performed action Y this month? We can also answer questions such as how many unique users have performed action X this week, today, or this hour? And then we can also analyze this, so we can compare users from different time. So for instance, we can say how many percentage of users that are active last week are still active today, or how many users that have played a song last week have still played a song today. And you can see that using this in your company or in your application will be very, very good, because you can do improvements and see how it affects your customers or your users. And you can also you can spot bugs with this as well. And it's just much more powerful analytics than just like counter tracking. Yeah. And the cool thing about Bitmapist is that it uses Redis and Redis Bitmaps. And using this, we can actually implement this in constant time, and we can implement this for millions of users. So you can scale this as you like. Of course, there are some things that this can't do, but then you can use other databases to solve this problem if you want. So what are bitmaps? Well, bitmaps is basically like a very, very, very dense bit structure, and it was introduced in, I think, 2.2 of Redis, so it's a pretty recent feature. And Redis basically gives us 4 commands or operations that we can do on this. One is set bit, the other is get bit, bit count, and bit up. So basically, set bit sets a bit of some key given a value, and get bit returns if a bit is set from some key and some value. And then, and this is one I really like, is you can do operations, like bit operations based on keys. So you can, this is where the retention analytics and cohort analytics come in place, because you basically compare bits. Yeah, and on Wikipedia you can read more about it, but it's really a simple bit structure. So how do you use this? Well, using it is really, really simple, and it's really, really fast. So you basically mark an event for, and it's generic what you mark. So basically you say that user 123 is active, or user 123 has played a song. And then you can use the in operator to figure out if user 123 has played a song this month, or has been active this month, or played a song this month. And then you can also use the len function to return how many users have done some kind of action this week or this hour and stuff like that. So you can see the actual API behind this is really, really simple. And the only thing you need is Redis 2.2 and importing this library, and then you just track stuff in your app that you're interested in, like most things. Because the more data you track, the more powerful analytics you can get out of it. And then the other, and this is like more powerful feature, is that you can actually do like bit operations, but these are more like set operations based on different things. So for instance, in this little code we answer how many users have been active last month are still active this month. Yeah. So this is how you use it. And one of the other things that this includes is cohort. So basically, using bitmaps, Bitmapist alone isn't really that powerful, I think. it's really using it in combination with cohort analytics. So basically, for our task manager, Todoist, we track different things. So for instance, we can answer this question: show me people who updated a task and then came back and completed a task. So you can actually do like set functions based on different actions. So you can answer like, show me users that have signed up and users that have played a song, or users that invited a friend. And then it shows you either daily or weekly or monthly stats and how they compare. So you can see here that on November 19, like 44,000 people have updated a task. And then 70% of these people completed one. I mean, it's not that interesting, but you can find a lot of more interesting stats to compare. And then you can actually see how this affects over time. So you can see on this day, 1 day after, 51% completed a task. 1 day after, 47, etc. So you can see actually evolution of the users and how actually like retention falls or rises. So I think actually more people should use these analytics because it just gives you a much better view of what your users are doing, and if they are coming back, and which features they are using most. Yeah. So these, and I think actually you can probably use Redis for more of these kinds of things, like advanced analytics that can give you an edge over everybody else. Yeah. So as the last, I would like to promote my new company, and basically we are like doing 2 tools, and we will do more task management and project management, and we are trying to like modernize how people work together. Yeah, and we are using a lot of Python, and if you are interested into challenges, we are hiring, so you should send me a message. Yeah. And questions and answers.
The bitmap storage is about the Redis implementation. What sort of storage requirements are there to scale it with the number of users that are there? So, if only 5% of your users have that bit switched, do you still need? Does the storage requirement of Redis require sort of allocate 100% of the user's space? Or is it
yeah. So it actually allocates based on the length or the length of the integer. So if you have like huge user IDs and you have to use integer-based user IDs, if they are huge, then it will allocate a lot of space. So if you have like, but I mean, it depends. I mean, usually it will be like megabytes on a million length integer or something like that. So it won't be that much, but still, like if you need to use this for millions of users, you still need to use gigabytes of data. But I think that's much, much less expensive than using something other, because there's no way you can scale this using gigabytes of memory in any other database. So, yeah.
So, how do you solve the problem if the data won't fit on a single machine for like cohort stuff? It looks like I'm not too familiar with the bit operations in Redis, but it looks like it basically joins like Z-union, the merge does, which means you can only do it on a single machine. Is that like easy to replicate?
I think actually, I mean, the thing that Bitmapist supports is every call supports a system. So you could use different systems for different types of data. But you're right that like you can't really do AND operations based on different machines. But actually, maybe with the Redis cluster, it will be possible because it just huge numbers that they are comparing, nothing else. So it should be a solvable problem. But currently, you need to use different systems to partition your data manually.
And would it just be the same as like you do the week event, or in the example here, the month events? Could you just pull down both keys and do the simple analysis? Like, is that all it takes?
Yeah.
Okay.
Yeah.
So it still would be fairly cheap if they lived on different servers.
Yeah. I'm pretty sure actually you could do this client side as well because it's just bit operations.
Yeah.
Show us. More questions? Okay, thank you.